So, ladies and gentlemen, thanks for coming today to this seminar, and thank you very much, Marines, for joining us in this series of seminars. It's a real pleasure to have you here today. Marines has a degree in physics by UC, but by the Complutense of Madrid, and and she's been doing his initial research in what is called today ESAC in Madrid, near Villafranca del Castillo. At that time, it was called the European Observatory of the Space Telescope. International Ultraviolet Explorer. And she did their PhD and postdoc. Then she moved in the late 80s, early 90s to Canada for a postdoc in Macmaster University, and then returned to Spain and became professor at UCM and now she's full professor. She's leading or the director of the Vacuum Ultraviolet Laboratory at UCM, Complutense of Madrid. She is teaching a diversity of topics, but mainly on astrophysics, geophysics, geodesy, plasma physics, etc. She's PI of an ERC advanced grant. I guess she's going to be talking about it today. That's about to start. Also, she's the PI of the Spanish participation in the International Space Telescope, SPECTR-UF, dealing with astronomical observation in the ultraviolet range. She has been working for ESA and NASA in the last decades, and indeed ESA appointed her as representative to the NASA Great Observatory Maturation Program in science, technology, architecture, etc. I mean, a lot of things, Inés. And I don't know what else to say here. I guess we can cut and keep going. Well, something that is important is that she's quite active promoting outreach, and she has been one of the founders of Hands-on Universe to help secondary school teachers to teach science, and I think that's also quite important. And nothing else. Please, floor is yours.
Thanks a lot
Thanks to you.
for the introduction. And you hear me well, perfect. Wow. Okay, so thanks a lot for the invitation, and thanks a lot for being here. We are all very busy, so taking some time to listen to someone else is really hard, so I appreciate it, and thanks again. Okay, so the talk I have prepared for you today is a description of what we have done to get where we are now and what we are planning to do in the future. Okay? So for you to understand better who we are and what we are doing, I have started by describing our projects in a chronological way. Okay? So we founded the Space Astronomy research group at the Complutense University. At the time, the regional government of Madrid started to create research groups within the university within the universities to give life to research lines that were smaller or different or interdepartmental and were not well described within what is the department structure itself. So we got there since the very beginning, and this came up because we have a very strong collaboration with the European Space Agency. Well, as my kind introductor was mentioning, when I finished my undergraduate studies, I moved into the European Space Agency. But at that time, the European Space Agency was the satellite tracking station named BILSPA, which was one of the satellite tracking stations of the European Space Agency. What happened is that at that time, the NASA, well, NASA, not really, the earliest steps in space astronomy of the European Space agency, started hand by hand with NASA with this project, which was the International Ultraviolet Explorer. And the International Ultraviolet Explorer was a satellite that lasted more than a decade, much more than a decade, in orbit, and that operated like a ground-based telescope. So it created a whole generation of people who used to go to a control center and manipulate an in-orbit facility until the facility point to that star, and the facility was doing that. And we were sat side by side of the observatory controller, okay? So the telescope controller. So it was a concept of a space operations center that has nothing to do with what is being done today. Today we have all these pipelines, and you have someone behind a computer that creates a pipeline, is launched, etc. At the time, it was done in real time, and we were sat by the spacecraft controller and the astronomer, resident astronomer, doing this kind of operations. So during my career, I started there, then I moved to the National Astronomical Observatory. In fact, I was working for like half a year for the INTA, and then I moved to McMaster, and then when I returned to Spain, I returned to ESA, to the European Space Agency, to this center, and from there, I became professor at the university. So we kept a very strong relation, and we have many collaborative projects. And that's why, as soon as this call was issued, we jumped into it successfully. The key project for us was this one, the World Space Observatory Ultraviolet. This observatory was built from that community that was created around this International Ultraviolet Explorer, this NASA ESA CERC mission. And it created a community that extended worldwide. Okay, we have people all over the planet, not only within the agencies, interacting and getting the data directly that were distributed there online. And we were seeing that the IUE was aging, and we knew that their end of life was coming. And then we started to move together and to collaborate to create a new mission that would be for everybody. And the idea was to convince United Nations to assist the maintenance of an observatory that was covering the ultraviolet range, and that would be the first of a series of observatories that will be covering the infrared, the X-rays, the optical range in a way that all the spectral range were always available to astronomers. Okay? Probably you are aware, but we cannot see ultraviolet, X-ray radiation, many infrared bands, many radio bands. We cannot see them from the ground, and we need to go to space. And the problem is that the agencies compete, and then they leave calls. For instance, now we have two X-rays observatories. We have Chandra from NASA, and we have X7 Newton from ESA. But in a few years from now, there will be none, because there is not X-ray observatory coming. We had IUE, and after there was Hubble, that was also in the optical. But after Hubble, there is no ultraviolet observatory coming, unless the flagship that is coming from NASA, this Habitable Worlds Observatory. So the idea behind our very broad thing was to promote this. And then we started creating this community. The leader of all of us was the director of the IUE Observatory, Willem Wonsteker, who unfortunately passed away too early. And we created this project. Well, at the end of the day, when you have to put money to really make it feasible, we ended up being 3 countries paying for the project. One is Spain, the other is Russia, and the other is Japan, JAXA. Okay? And what were we doing, or what are we doing, in fact? we are building a 2.5 meters space telescope. And I think, this in here, perfect. So this gives you the scale. This is the structural and thermal model of the telescope. So it's a nearly 2 meters telescope. It's 1.7 meters primary telescope with weights tons. It's in the scale of the ton, and which is one of the key projects of the Russian space program, science space program. Russia has its own science program, and its science program had 3 projects for this period. The first one was in radio frequencies, and this worked beautifully. It was the first telescope to do interferometry space ground. Then the second is Spectrum X, and this is flying now very well, and it has a German instrument, which is eRosita, that has been turned off already for 2 years since the Ukraine crisis, and only the Russian instrument, which works in high energies, is being operated. And then the third one was Spectrum UF for ultraviolet, and this is the name of the telescope within the Russian program. So this is, in fact, the major collaboration between Spain and Russia in space science. It came after the signing of an agreement by our foreign affairs ministries in 2006. And well, we have been working together and getting to the point that today we should be integrating our instruments together, but well, I don't need to say more about that, okay? But this gives you an idea of the team and the people involved and the many years that we have been working on that and getting ready for a launch that obviously is going to be delayed. So here we have the 2 main instruments. It's a UV spectrograph, and that has 2 components, a long slit spectrograph and a high resolution spectrograph. And then we have an imaging camera, and this imaging camera is the contribution of Spain and Russia. This is a joint instrument, and the Russians are taking care of the near ultraviolet branch, and we take care of the far UV branch, which is one of the 2 optical paths in this instrument. The Japanese instrument is over there. It's a small instrument dedicated to the detection of oxygen in exoplanets, only that. Our instrument is much more versatile, and well, we have our camera, this camera unit, the far UV channel was designed by us. The detector has been developed in Spain, is ready to be flown, nearly ready to be flown, but obviously we cannot transfer any hardware to Russia, okay? So we have been involved in hardware development. This is the optical system, and we also were providing optical elements like filters and prisms to analyze the light. We developed this laboratory, and in this laboratory we developed this simulator of the optical beam of the telescope to test the performance of the optical elements. And which were the end results of that? The end results is that nowadays we have a laboratory for vacuum ultraviolet instrumentation, which is not available elsewhere in Spain, and there are very few in Europe and very few all over the world, okay? I can, then when we get to the questions, you may ask me for the questions if you feel curious about that. We also developed operation centers and science operation center. And in fact, we passed the test of the Russian Space Agency to operate Russian missions from our grounds. And we are credited by them to do that, which is quite unusual. Probably you know that there are not other places where the Russians accept that a foreign entity operates missions. Okay, and well, this is our setup with the control room, where we are currently running other experiments, because obviously it is not, WSO, it is not flown yet. And we have implemented in software all this system. I mean, it's not only the nice screens with some displays, but it is also all the software that is behind it. And we are also involved in proposal planning, and we have reused some of the components to use our antenna. This is the antenna we already have, which is a small radio telescope that we use for education and for tracking the solar activity, monitoring the solar activity. But we have acquired recently another antenna, which is not shown there, that it is to get signals in the X bands from the radio amateurs, and to be able to download data from CubeSats, because we are involved in some CubeSat projects. So, as I said, we started with the World Space Observatory. From there, we have a community, which is the Network for Ultraviolet Astronomy, which has like 500 astronomers all over the planet, most of them in Europe and in the US. We also created an instrumentation, which is a laboratory around the far UV imager, and we created a ground segment SOC. And this was the first generation, just World Space Observatory. We created that from them. And then here comes the second generations. We have the operations of our small radio telescope control from our software and our operations center. We are running a project to use the magnetometers of CubeSats to monitor the variation of the Earth magnetic field. You know that the magnetic field is varying quite rapidly, so this makes sense. And there are plenty of CubeSats, so it's a very interesting application of an attitude control instrument for science, especially now that the patterns are changing so much. We have created a UV source catalog that serves the worldwide community. And this is one. We have created our laboratory for vacuum ultraviolet instrumentation. We have this far UV detector that is now ready to be used in, hopefully, WSO UV, but if we cannot use it there, at least we will have it for other missions, and it's a unique detector. We have managed to get a quantum efficiency that is 3 times the usual values, okay, which means a lot in the UV range. And then, well, from the UV community, we have grown within the International Astronomical Union, the IAU, and created a UV astronomy working group. And now we are creating, in fact, we have a meeting this afternoon to promote the creation of a commission on space astronomy within the International Astronomical Union, which didn't have it. So that's the kind of networking and people we work with. And also we have contributed with some colleagues, the Lobby Lunar Latino, which is something we are very proud of. And we are working with colleagues in Mexico, in Colombia, in Chile, and Argentina to put in a small mission on the moon. And we have already a working design that we are adapting to fit into a 12 units CubeSat to be launched with one of the NASA launchers, these ones that are making the frequent flights to the moon, to set this small telescope on the moon, in lunar orbit, in fact. And also, we managed the proposal for a large European ultraviolet optical observatory, and that's how we are also being part of this flagship NASA mission, which is the Habitable World Observatory, which is intended to be a telescope of 8 meters, so larger than James Webb, but that works in the ultraviolet range, able to obtain the first image of an Earth-like planet outside the solar system. That's the target. Pretty ambitious, okay? And so this is it. And this is this is just some images showing our facilities. This is the proposal for this CubeSat concept, and this is some images from our observatory. And obviously, we are involved, and we are called for several missions, and we are participating in different stages of development in all these missions. That if you feel curious, I can talk to you, but I will not get into that now. Okay? Okay, and well, this is just an image of our lunar ultraviolet observatory I wanted to share with you, because we use the experts of the WSO, both in the in terms of optical elements, but also in terms of the detector. And the project is quite advanced now. And our objective is to set it in lunar orbit. This is basically the structure we have in mind. And we are working on that with some public and also but private agencies on doing that. We have been working on missions like Castors, like Laputa, like Aerospace Hub, where we have participated into several activities related with promoting the transfer of knowledge from the university to the industry. And this is the project we lead now, which is Uriel, which comes from Ultraviolet Researchers for the Investigation of the Emergence of Life, which has a broad consortium behind. And this is the project that is associated with this ERC research grant, that advanced grant, that is related with astrobiological research. And this is the project I will talk more about now. So let's go now into astrobiology. Yeah? I think that now you have a pretty good idea of who we are, what kind of things we do, and what kind of capabilities we have. And then let's go to this. Okay, this that you see in this plot is a summary of what we know about the creation of proteogenic amino acids by natural means. Okay, what I mean by natural means that we are not producing them in the lab, we are not using other organisms, we are just using gas and materials. No? There are, the first experiment was the experiment by Miller. You are all familiarized with that, it's sketched here. You put in a bubble, you put methane, ammonia, water, you mix them all, you heat them, you produce electric discharge, and you make, and then you condense, get here some residue, and go back again. After some time in the residue, you find that from all of this, you get glycine and alanine and aspartic acid, which are all amino acids. Okay? And that's the very beginning of the story. Well, many years after, in the 2000, many people started to work in a different approach, because we were analyzing meteorites, and in the meteorites we were finding many amino acids, and they had to come from somewhere. So we started to test in the lab whether irradiation, UV irradiation of ices, like the comet ices, etc., could result in the production of amino acids. This started basically in 2000. The first seminal work was by two co-authors. I have selected here, I mean, there were two articles coming up at the same time, one European and one US-based. And I have put here the European one. And they were the first to find that these amino acids, so you could produce the same that Miller was able to produce and more, can be produced through the processing of space ices by UV light. Okay? These experiments keep on going, and then other versions of a Miller experiment were run that tried to simulate the situations in early Earth, the environment in early Earth, and they managed to get more amino acids. And this is some results from a similar experiment in the branch of the space ice. And you see that you can produce other. So you have there a fingerprint in the mixture of proteogenic amino acids you managed to get that depends on the procedure you use to produce them. Okay, and that's very interesting. Okay, this process kept ongoing. This investigation on space sizes kept on going, and just like a couple of years ago, in the nucleobases were synthesized for the first time. Okay, so there was a lot of work starting from the pure raw materials, methanol, ammonia, ammonia, and water, and doing mixtures and processing them in different manners. You managed to get all the ribols, all the desoxyribols, all the steps, chemical steps, to get finally the nucleobases. And last year, the Japanese mission, Yababusa, was able to detect for the first time one in a comet. So it seems that everything goes in the same sense. So currently, on Earth, we don't know whether our amino acids come from space or come through some bizarre procedure on Earth. We don't know, okay? And this is where a lot of research is ongoing. So the astrobiological research is limited. Why is limited? Because we can do many things in the lab, but we need to confront these lab measurements with actual space measurements. Okay, getting to the Rosetta mission costed hundreds of millions of euros only for one measurement. Okay? And the Comet Interceptor mission, which is coming for ESA, is trying to do something similar for another comet. And it's going to cost hundreds of millions of euros. So going there to take samples, to analyze them, is fantastic, but it's incredibly expensive. You will not be able to get a statistical vision of what is going on. You have nothing, okay? So what would happen if we could measure the abundance of amino acids remotely? That would be a giant step, okay? So this has been attempted for many, many, many years. And the problem is that even the simplest amino acid, glycine, remains evasive to detection. Why? Because detection is attempted in radio wavelengths, and in radio wavelengths, the amino acids signatures, spectral signatures, get confused with the signatures of other molecules that are in the same place. So it's very difficult to say, I have detected glycine. You cannot say that easily. And there have been many attempts, a lot of money put in there, no? So the proposal I made to the ERC, and that they agreed to finance, is to seek for another way to detect amino acids. And this is, instead of using the radio signature, use the ultraviolet signature, okay? I don't know whether you are familiarized with laboratory work on proteins, amino acids, all these kind of things. But what they do typically is they have a UV lamp. They put these proteins or amino acids in solution within it, and they pass the UV lamp, the radiation, and any protein, any amino acids is optically active. Well, most of them, not all, but most of them are optically active, and through the degree of activity, which means basically that the UV light is polarized, linearly polarized, and you measure how much the polarization angle has been rotated, you determine the abundance. And you detect whether there is any enantiomeric imbalance between the right hand and the left hand of the two enantiomers, okay? And this is routinely done in the laboratory, but was never attempted in space. So that's what we are trying to do, okay? That's our objective. We will try to detect remotely alanine, through its optical activity. And you would ask me, why alanine? Well, because as you see here, the second most abundant amino acid produced in all cases is alanine, and is the most abundant amino acid which is optically active. So it's the obvious one to try to detect. This that you have here is condensed in a picture, all the information we have. So it's not much, okay? This that you have here is the amino acids found in meteoritic samples. Here you have all the meteorites, absolutely all. And here you have all the amino acids detected, okay? And the color code relates with the abundance, okay? So here you have some amino acids, some meteorites, which are especially abundant in amino acids, and others that not. And also you have some bizarre molecules that you would not expect in a normal amino acid composition, and that the people think that come because meteorites, the information on the meteorites comes thermally processed by the atmosphere, because they have to do the re-entry, they heat up, and this may change the composition. So some things may remain, but some additional components may be produced. So this is what we know, okay? And this is alanine. So alanine is a molecule that has an arm, one asymmetry, okay? So it comes in two different positions. It's like the hands. You may have your left hand and your right hand, both are hands, but if you try to overlap them, no way, okay? Because one has this leg on this side, and this other has the leg on the other, so overlap is unfeasible. This results in different activity of the propagation of light, okay? Right-handed or left-handed may prefer to propagate more light polarizing one direction or another. Or if you put into the system light that is unpolarized, it will propagate better light polarized in a given direction. It works like a circuit. Okay, and this is the beautiful thing about alanines. It has a very, very strong effect in polarization, and it has it at 180 nanometers, okay, in the ultraviolet. So what we need to do is to design a telescope that measures ultraviolet polarization in this band, and if we find that there is ultraviolet polarization only in this band, we will know that we have alanine, okay? We will also know that we have not the same abundance of alanine left-handed and alanine right-handed, because if there were exactly in the same abundance, then you wouldn't see anything, okay? So, and this is to show you that we are not crazy, okay? Because the information we have from meteorites is that equilibrium is not observed between left-handed and right-handed in any meteorite, okay? And in fact, what we found is typically that most meteorites have excess, which is above 10%. Yes, there are some few with very low values, but most of them don't. And this is in actual measurements, and this is the signal we expect to detect. These are the Stokes parameters. I can tell you more about that if you wish. But this is basically, this is telling you the signal that we are expecting to detect, and what we are expecting to detect is a rotation of the polarization angle of the order of 5 milliradians, between 5 and 10 milliradians, which is of the order of 30 arc seconds or half an arc minute. That means that we have to be very, very sensitive and not lose information in the process and manage with the noise, okay? So it's not as trivial as producing this nice ultraviolet spectropolarimeter, put it in orbit and measure it. We need to understand better whether the rugosity of the materials will affect these measurements and how this will affect it, how the crystals will be produced, the alanine crystals, whether it will come up in crystals, whether it will be another kind of things, whether we'll have mixed crystals with anything or whatever, yeah? So that's why we asked for this grant. This view graph summarizes all the methods used to detect amino acids in space, to really take the astrobiological research to a next step. And there you have the analysis of meteorites, which is fantastic. But we are limited in the sense that you don't decide which samples you study. And also the composition may be affected by the impact, and you also have to take care of possible contamination with Earth-based amino acids. You have the space probes to comets, which are very nice, but they are very expensive, very low efficiency, and as today, they don't measure amino acids, but they measure the results of the photodissociation of glycine, which is the only amino acid, which, well, it's not the only, it's the most abundant amino acid, but it's not chiral. So you cannot measure any imbalance. Then you have the remote detection through radio wavelengths, glycine, which would be wonderful, but we have these problems, these detection problems. And there it is, the proposal, our proposal, which has an inconvenience that the signal that we are expecting is low. I am telling you that we are looking for rotations of the polarization angle of 30 arc seconds or half an arc minute, okay? Which is quite a deal. But we have plenty of targets for remote observation. This is just a view graph showing the distribution of the asteroids and minor bodies around the Earth. This is 2 astronomical units, which is 2 times the distance to the Sun and the Earth. And this progress, 5.2 is at Jupiter level. And you see all these bluish things are carbon-based amino acids, and there are carbon-based asteroids, and there are plenty of them. So if we were able to design this instrument and it was feasible to measure, we will have one mission navigating in space and thousands of targets at once. Okay? So what we need to do is to measure, prior to getting into this instrument building, we need to measure the structure and the spectropolarimetric signature of the dirty ices that will be there. And we also will need to measure some the impact of other possible impurities in their optical performance, like glycerin, graphitic particles, all within a water ice matrix. And also we need to evaluate the impact of granularity and surface irregularities in the detection. Okay, and this is something that we are equipping our lab to do. Yeah, this is basically our work plan. I will go fast on that. If you want, I will go back to it. But basically, we have a 5-year work plan. And this is the impact we expect to have. So the impact of our research will be enormous, but not only on astrobiology itself, but also in our understanding of universe biology, because it will mean that the universe itself is an industry producing bio things. No, it's not only producing metals or planets, it's also producing biostructures that are first generated in space and then rain down into planets where they may germinate or not. That also means that the mechanism would be rather universal. And this means that if we travel to this exo-Earth we are trying to image with the Habitable Worlds Observatory, if we see plants there, they will be rather similar to ours. And the only thing that we will need to check is that their chirality is the same than us, because if not, we can confront all sorts of problems. Okay? But this will be the only thing. to check. And we will be biocompatible. It also has interest in chemistry and pharmacology because we are going to study crystallization of alanine and alanine mixtures. And you know that, for instance, alanine is used in materials science also as a building block for more complex amino acids. We are going to develop for the first time in 70 years a far UV microscope. Far UV microscopes were initiated in the 50s and rapidly overcome by electron microscopy. Obviously, that you can produce much better resolution, etc., etc. But this far UV microscope can get images with angular resolutions, with scales of resolutions of the order of 0.1, 0.2 microns, and can use the very same light that they use to illuminate the sample, to photoprocess the sample, and understand how UV radiation affects materials or organic tissues, okay, which is very interesting. And the end use is also to develop this compact and sensitive UV spectropolarimeter that we can use for the mission named Uriel that we are already proposing to the European Space Agency. And I think this is all. Thank you very much for your attention. I am from Vitoria. This was not said. And I couldn't avoid putting this in there. Yes, that was the first plane built in Spain with Spanish technology. Okay, it was flown from the small airport in Vitoria. And the only thing that was not Spanish, because the design was done by Heraclio Alfaro himself, is the engine. That the engine came from an aviation fan from Guipúzcoa, who had taken the leftovers of a crashed airplane from France, and he passed the engine to Heraclio Alfaro to build this plane. But the rest of, including the design, this tail here, which is this negative slope, was the first time that was ever tried to grant longitudinal stability. Okay, so yes, just for you to feel proud.